Okay, let's think about these clicker questions here. How would the entropy change if the ionic charge increased? Well, we can imagine this particular situation. If we have an ion with a fairly weak charge versus an ion with a fairly strong charge, then near the weak ion, then the solvent molecules are going to not be all that affected. Those dipolar solvent molecules are not going to be so affected by that weak ion. But to the strong one, all of those dipole solvent molecules are just going to be lined up ramrod straight, pointing towards that ion. So as you can see, that is going to be a decrease in the entropy. So the entropy is going to decrease. This is supposed to say radius, okay? And this is supposed to say increased. I realized that mistake just now. So now we ask, if we have the same charge, but we have ions of two different sizes, well, the effect this is going to have is the smaller radius is going to allow those ions to get closer to the center of that, or it's going to allow the solvent molecules to get closer to that ion, whereas out here, they're going to be far enough away that the force imposed on them is not going to be so strong. So actually increasing the radius is going to increase the entropy. Okay, I've dedicated this slide to introduce a number of different terms that we're going to be using for the rest of the chapter. And I think it would be most helpful to consider a couple of different example reactions. Okay, so for our first example, let's say that we have hydrochloric acid gas and it's dissolving. So we have H plus aqueous, Cl minus aqueous. All right, our stoichiometric coefficient plus is what corresponds to the positive ion. And as you can see, our stoichiometric coefficient for the positive ion is going to be 1. And what is our Z plus? Well, the Z plus is just the charge that's indicated right up here in the upper right-hand corner. So that's going to be positive 1. And then over here, for Cl, our stoichiometric coefficient is 1, and our Z minus is negative 1, because that's indicated by this charge right here. Let's see another example. Magnesium chloride dissolving into water again, Mg2 plus aqueous, 2Cl minus aqueous. Let's assign these variables here. Nu plus becomes 1 because there's just one magnesium in this reaction. Our Z plus is actually positive 2 for this one. Nu minus is 2 in this case. And our Z minus is, again, negative 1. So just want to make sure that you understand what the nu and the Z mean for the remainder of this lecture. I want to introduce next the ionic strength. It's a quantity that we're going to use a number of more times in this lecture and also in our homework. And the ionic strength is defined as the molality divided by 2. So this is molality of electrolyte. And remember, the molality is the moles of solute per kilogram of solvent. I know it's annoying to have to switch back and forth between molarity and molality, and I'm right there with you. I know it's annoying too, but this is just the convention that they use, so we've got no choice really. We just got to be able to switch back and forth easily between molality and molarity. Okay, and then we have a summation over all of the different electrolytes. Okay, and then the stoichiometric coefficient of the positive ion Z of the positive ion squared plus stoichiometric coefficient of the negative ion times Z of the negative ion squared. And I can enclose all this in parenthesis right there. But most of the time, only one electrolyte is present. One electrolyte's species is present. So like HCl or MgCl. Then in that case, our ionic strength is the molality of that solution divided by 2. And then the summation goes away. We just get the positive stoichiometric coefficient, the positive charge, negative stoichiometric coefficient, negative charge, like so. Okay, now we're going to apply what we learned in the last chapter about chemical potentials and activities of non-ideal solutions to electrolyte solutions. And to begin, we'll need to consider the chemical potential of an ion, or one of the ions in solution. And as usual, that's going to equal the standard state of that ion plus RT log activity. Unfortunately, it's not all that useful for us to just consider one ion at a time. It's convention to consider all the ions at once. So we're going to be lumping a whole bunch of different quantities into single values, and that's because it will be experimentally possible to measure all those values lumped together and not, for instance, the individual chemical potentials of individual ions. So we're going to consider the chemical potential of the whole solute. So that means the both the positive and the negative ions. And this is going to equal the stoichiometric coefficient of the positive ion times the chemical potential of the positive ion, which, by the way, is just synonymous with that quantity that we have right there. The stoichiometric coefficient times the chemical potential of the negative ion. And that is also described by that formula right there. And that's going to give us a new type of chemical potential, and I'll give you the name for this in just a moment, but that is going to be this mu solute divided by nu, and I'll define nu right here. This nu is the stoichiometric coefficients just added together. Okay? It's going to be the nu plus mu plus, I'm taking this from up there, by the way, plus nu minus mu minus. And then down here we have that nu right there, so we get a nu plus plus a nu minus. And this is called the mean ionic chemical potential. And again, the reason why we're going to all this work to combine all these things is it's not going to be possible for us to measure the chemical potentials of the individual ions. We can only measure the combined chemical potentials of the entire solute. Okay? So, if I told you that the stoichiometric coefficient of a particular ion times the chemical potential of that ion equals stoichiometric coefficient of that ion times the standard chemical potential of that ion plus RT log activity, it's going to be raised to that stoichiometric coefficient, because remember, the rules of logland allow us to exchange those two locations. And then this, of course, is just going to go right up into that expression there for both the positive and negative ions. And so what that's going to give us is this mu plus or minus is going to equal a sort of standard mu plus or minus plus RT log this activity plus or minus. This is called the mean ionic activity, and it just equals A plus minus A plus raised to the positive stoichiometric coefficient. Oops, that's not A plus. It's A times A minus nu minus to the power of 1 over nu, like that. Now, keep in mind that the purpose of all of this is so that eventually we'll be able to find an expression for the equilibrium constants. So that's what we'll get to in the next video or two. But first, I want to do the final step in defining this activity. This A plus minus, mean ionic activity, is going to be equal to a molality plus minus divided by a standard molality multiplied times something like an activity coefficient. So let me define each of these terms. This molality plus minus equals the molality of the plus ion, coefficient of the plus ion, times molality of the minus ion, coefficient of the minus ion, and then this 1 over nu again. And I know, it's so annoying that we're switching now to molalities and not using concentrations, molarities. But again, it's just convention, and we need to be able to think on our feet in this way. And I know we didn't talk about molalities with respect to the activities in the last chapter, but you would just use the exact same arguments as you did for concentration. And you would see how the activity relates to the molality this time and not the concentration. You'd have a different activity if you wanted to deal in units of concentration. And then this m naught, a standard molality, is defined as 1 mole per kilogram. And so that's what gets plugged in right there. But this guy right here, this is the one, this gamma plus minus, which is the mean activity coefficient. We can find this. We can calculate it directly. So for the first time, we'll actually see a theoretical framework for how to get that gamma value, that activity coefficient. And that's what we'll see in the next video.